Hello and welcome to the Terran Space Academy. My first car was a 1968 Cadillac Sedan DeVille, but my second car was a 1966 Pontiac Executive Star Chief. The Star Chief was only made for 1 year, while the Pontiac Executive was made for about 4 years. It was old when I bought it, but it had a glass steering wheel and was a beautiful vehicle. I went back to my hometown not long ago and saw one exactly like it. The owner walked up while I was admiring it, and we got to talking. He said some idiot kid had traded it to his brother in the 1980s for a motorcycle. I laughed and told him that idiot was me. I couldn't afford the gas burned by the massive 400 cubic inch displacement 390 horsepower engine. They made a lot of neat things in the 1960s, including this, the Saturn V. To this day, the most powerful rocket to ever launch, at 35,100 kilonewtons. If the SLS ever gets off the ground, it will produce a little more thrust at about 36,640 kilonewtons, if it ever gets off the ground. But I think long before the SLS flies, this guy, the Starship Super Heavy First Stage, will produce 65,000 kilonewtons of thrust and set a new standard. But let's look back and see if a Starship was possible before now. Please don't forget to like and subscribe. Tuition is voluntary at patreon.com/Terran Space Academy, and merchandise is available on eBay. We always appreciate your feedback and are constantly working to improve our equipment and courses to help prepare you for a bright future in the space industry. For that reason, we're going to try to upgrade our software to have higher resolution imaging for the next year. Any contribution you can make will be appreciated. Thinking about how cool my old car was got me thinking about the technology available when it was built. And I started wondering, could the second stage of the Saturn V been modified to have flown like the Starship and come back to land? Relanding a spaceship is not easy. The Saturn V second stage was called the S2. It was hydrogen powered. The only reusable hydrogen powered rocket flying today is the new Shepard by Blue Origin. The new Shepard is not a large spacecraft, but it does reach the von Karman line. Here you see it in action. And here you see the landing legs deploying. The new Shepard works well for suborbital flight, but is quite small, with a mass of only 20,500 kilograms without fuel and about 75,000 kilograms with fuel, according to Astronautics. The Starship is much larger than the new Shepard. At 50 meters in height and 18 meters in diameter, with a gross mass of 1,320,000 kilograms, it is the largest second stage ever built and is more than 17 times the mass of New Shepard. There is no real comparison between these two. But the Saturn V second stage, built by North American Aviation, had a height of 25 meters and a diameter of 20 meters. It had a dry mass of 36,200 kilograms and could hold 443,000 kilograms of propellant with a total gross mass of about 480,000 kilograms. It was called the S2, and we'll refer to it that way from time to time. At more than 1/3 the mass of the Starship, we can start comparing these. The S2 had 5 of these Hydrolox engines called the Rocketdyne J2, with a vacuum thrust of 1,033 kilonewtons each and a specific impulse of 421 seconds in vacuum. Now pause for a second. The BE3 Hydrolox engine used by Blue Origin on the new Shepard has a thrust of 490 kilonewtons and a vacuum thrust of 710 kilonewtons. This does not seem like a great improvement. It can be throttled down to just 89 kilonewtons, which is good for landing. And vacuum thrust and efficiency is not sea level thrust efficiency. Some sources report the sea level efficiency of the J2 to be only 200 seconds specific impulse, while the vacuum version is 421 seconds. I found this hard to believe, but when I double-checked my equations, showing force, 1,033 newtons, divided by ejection velocity, which is specific impulse times the force of gravity, or 421 seconds times 9.81 meters per second squared, I came out with 250 kilograms per second. Then, assuming the same fuel flow at sea level takeoff, with the thrust given by Rocketdyne at sea level of 486 kilonewtons, dividing this by the same fuel flow, we get 198 seconds. This shows that vacuum optimized engines don't work well at sea level, but the J2 was never meant to be used at sea level. Let's look at a Hydrolox engine that was. The RS-68A is flown on the Delta and Delta Heavy rockets. The RS-68A is built by Rocketdyne and is used on the Delta IV and Delta IV Heavy rockets still flying today. Rocketdyne had built the RS-25 for the space shuttle, and while efficient, these engines turned out to be expensive. Too expensive to throw away every launch. Now the SLS plans to throw away 4 of them per launch. Anyway, the RS-68 has a gas generator power cycle like the planned Blue Origin BE-4. It has about 10% less efficiency than the Space Shuttle main engine, but 80% fewer parts. It was developed in the 90s to make a simpler, cheaper, heavy-lift engine. The A version is just optimized and improved in small ways that add up to higher efficiency. Rocketdyne gives the performance of the RS-68 as 2,950 kilonewtons at sea level and 3,370 kilonewtons in a vacuum. This is an improvement of 14%. The mass is 6,600 kilograms, giving it a thrust-to-weight ratio of 51.2 and a specific impulse of 410 seconds in vacuum and 365 seconds at sea level. The difference between sea level and vacuum efficiency for the Raptor is 330 seconds to 380 seconds. This is also only a 15% difference. To maximize a rocket engine for vacuum operations, the main thing you have to do is put on a much larger nozzle. Let's look at why this is. Pressure exerted by a gas is usually in all directions. Due to gas molecules striking the walls of the chamber holding them, pressure is exerted. Heat a gas up, and because heat is just our name for kinetic energy in a substance, the molecules move faster, hit harder, and exert more pressure. Squeeze a gas in a piston and the gas heats up as there are more impacts per second due to the confined space. The pressure you can operate your engine at is the main determinant of efficiency for a rocket engine. The higher the pressure, the better. C star is the variable we assign to the theoretical efficiency of a combustion chamber. It would be the exhaust velocity disregarding outside pressure and nozzle design. Think of it as the ejection velocity at the throat of the rocket engine seen here. C star equals the pressure in the chamber, P1, times the throat area, AT, divided by the mass flow rate of the propellant, M dot. Most companies don't give us the engine throat size, but we can calculate it. We know the world record for rocket combustion chamber pressure was set not long ago at 310 bar by the Raptor engine, beating the previous record held by the RD-701. At that pressure, the rocket engine produced 2,210,000 newtons of force. We know that 1 bar equals 101,325 pascals, so 310 bar equals 31,410,750 pascals. Now we have force and pressure. Now we just need the mass fuel flow to figure out the throat area. We call up a previous equation showing that thrust equals mass flow rate times ejection velocity. We can find that the highest specific impulse for a Raptor is about 380 seconds in a vacuum. We can turn specific impulse back into ejection velocity by multiplying by the force of gravity on Earth, 9.81 meters per second squared, and we get 3,728 meters per second. Putting this into our equation gives us a mass flow rate of 593 kilograms per second. Let's compare this to someone else's calculation to double check. Remember this diagram? Here we see 133 kilograms per second of methane going in and 493 kilograms per second of oxygen going in here to produce 2,050,000 newtons of force indicated here. That adds up to 626 kilograms per second, so our numbers are off by only 5.5%. We plug our answer into the equation and we get an area of 0.081 square meters. By using the area of a circle and solving for radius, we get about 16 centimeters, or 6.5 inches. So every second a Raptor operates at full power. About 600 kilograms of propellant goes through a hole about a foot across. That's crazy. But at 3,728 meters per second, it makes sense. Now in the combustion chamber, the pressure is in all directions, random, and the molecules are moving at subsonic velocities. But as they get compressed through the throat of the engine, they reach the speed of sound for that gas at that pressure and temperature in that confined space. Then they exit and expand and become supersonic. Now we have taken the kinetic energy of the heat and pressure of the combustion chamber, which was in all directions, and turned it into ejection velocity of the propellant in one direction. This gas will have a high pressure in this direction, blasting concrete apart. But according to Bernoulli's principle, a gas moving faster in one direction has lower pressure in directions opposite to it. The pressure exerted by the sides of this column of fast-moving propellant is weak. This allows the pressure from the outside air to compress this column from the sides. If an engine is not optimized for sea level, you can actually see the column of hot, fast-moving propellant taper instead of flaring, sometimes to the point that these molecules start reflecting off of each other and flare out again, as you see here. This pattern can repeat along the column of gas, and we get what are called shock diamonds, seen here. You can also have the pressure from the outside air pushing its way into the nozzle. This would be an overexpanded nozzle, meaning the nozzle is too long for atmospheric use. This boundary layer separation inside the nozzle creates instabilities that can destroy your engine. The Space Shuttle main engines had a unique shape so they could function at sea level and in vacuum. They have tried to make adjustable nozzles, seen here, but these aren't efficient and have a lot of mass. And please don't send me 400 posts on why an aerospike engine would solve these problems. It would, but you would have to solve the problem of the aerospike melting, and no one wants to invest the money to do it. If you look at a sea level Raptor compared to a vacuum Raptor, you will see that the only real difference is the size of the nozzle. If you make your nozzle too short, you will have an underexpanded nozzle, shown here. Then you are wasting energy. That is why the Starship will have 6 engines eventually. 3 are sea level optimized, with much smaller nozzles, and 3 are vacuum optimized, with much larger nozzles, seen here. Now back to our classic 1966 Starship. The J2 was designed for use in space and never optimized for sea level operation. Since the maximum thrust of the J2 is supposed to be 1,033 kilonewtons, we will use that figure. Since other Hydrolox engines like the RS-68 lost about 14% efficiency, we will take that off our thrust for sea level and get 888,000 newtons. Let's go with 880 kilonewtons to be safe. The engineers arranged these 5 engines in what is called a quincunx or cross formation. The other engines could gimbal, but the central one did not. They had a common bulkhead between the hydrogen and oxygen tanks made of aluminum with a phenolic resin, which is a type of early plastic used in bakelite, as an insulating separator. The liquid oxygen tank held 310 cubic meters, and the hydrogen tank was 980 cubic meters, which, with the density differences we have discussed at 1,157 kilograms per cubic meter for liquid oxygen and 71 kilograms per cubic meter for hydrogen, gives us 359 tons of oxygen and 69.5 tons of hydrogen, giving a total propellant mass of 428 tons. The oxidizer to fuel ratio for the J2 was 5.5 to 1, and if we divide 359 tons by 69.5 tons, we get 5.15, so again we are close. We double check the reported propellant mass of 443 tons and see that we are in the ballpark with 428 tons. I'm using NASA numbers, so I don't know where these discrepancies come from, except that some will be estimates and nothing runs as efficiently in real life as it does on paper, and there's always a margin of error. Also, almost all chemical rocket engines run fuel-rich, which improves their efficiency, especially for hydrogen-based chemical engines. These rockets will also have a propellant for small engines that fire to bring the fuel and oxidizer down to the bottom of the main tanks when in free fall so it can get to the pumps. These are called ullage rockets and can be seen here. So could the Saturn V second stage, using 5 sea-level optimized J2 engines, have lifted itself off the ground like a Starship? Let's compare the 2 engines again since we've ran through a lot of equations. The Saturn V J2 second stage engine, first flown in 1967, had a higher specific impulse than the Raptor, which is fueled by methane. That is to be expected, since specific impulse is limited by the heat of combustion and the ejection velocity of the products of combustion, what we call propellant. Of all common rocket fuels, hydrogen is the most efficient, but not the easiest to work with. Remember, it must be kept at 20 Kelvin, and because of its low density, needs a very large tank. The Saturn V second stage, or S2 as it was known, had a mass of 480,000 kilograms fully fueled. With a mass of 480,000 kilograms times the gravity of Earth at 9.81 meters per second squared, we get a weight of 4,708,800 newtons. We have a total thrust of 5 times 880,000 newtons to give us 4,400,000 newtons, and if we divide the thrust by the weight, we get a thrust-to-weight ratio of 0.934. We do not produce enough thrust to get this guy off the ground, even if we were to increase the engine to full throttle and risk blowing them up. So we stop there. We would have to add more J2 engines, which would burn more fuel and oxidizer, so we need bigger tanks, which would add more mass, and we would have to calculate everything all over or save mass somewhere else. or we can run things backwards. We need a thrust-to-weight ratio of 1.5 from an optimal launch. We also see that the Saturn V second stage is only half the height of the Starship. Let's stretch it out to a full height of 50 meters and just double our tank size. Stretching a tank does not quite double the mass, but let's double our actual gross mass and start from there. Now we have a total mass of 960,000 kilograms. Let's use a 95% propellant to dry mass ratio and get a dry mass of 48,000 kilograms and a propellant mass of 912,000 kilograms. To lift off, we need more engines. So if we have a mass of 960,000 kilograms at takeoff, we have a weight of 9,417,600 newtons. If we want a thrust-to-weight ratio of 1.5, we need a total thrust of 14,126,400 newtons. If our engines produce 880,000 newtons at sea level, we will need 16 engines. Okay, we are starting to look a little like the Soviet N-1 moon rocket that failed because adjusting fuel flow to all those engines was a problem. Their system was designed so that if one of the 30 NK-15 engines went down, the opposite engine would shut off also to stay balanced. But without modern sensors and electronics, the control system could not react fast enough to an engine out. So when one had a problem, the ship would overreact and starve some of the others, causing their opposite engines to also shut down, and then we fall out of the sky. But the Americans had better sensors and faster computers, so let's look at our 1966 hydrogen-powered Starship. It has a gross mass of 960,000 kilograms and an empty mass of 48,000 kilograms. We need a delta V of at least 11.2 kilometers per second to get into low Earth orbit. The rocket equation tells us that delta V equals ejection velocity times the natural log of m1, starting mass, over m2, final mass. We know that our ejection velocity is specific impulse, 362 at sea level and 421 in space, times Earth's gravity at 9.81 meters per second squared, gets us 3,552 to 4,130 meters per second. Let's average that to 3,840 meters per second. If we divide m1 by m2, we get 20. The natural log of 20 is 3. Multiply 3 times the ejection velocity, and we get 11,503 meters per second, or 11.5 kilometers per second. Since we started off stationary, we can ignore that you add the initial velocity to this equation. Clearly, we could just barely get to low Earth orbit. We might, in fact, have enough extra to come back and land if we skydive like Starship does to burn off kinetic energy. So we apparently had the technology in the late 1960s to build a low Earth orbit or point-to-point Starship. We definitely had the same capabilities in steel, or at least very close. We could have had intercontinental flight times of about 30 minutes, instead of the 14 hours it took me to get to Australia. Now granted, this thing would not be able to carry much payload, but 100 people with an average mass of 70 kilograms would only be 7 tons. Launch it from Europe to Australia once a week for rich people, totally reusable. People paid $12,000 each to fly on a Concorde in the 1970s. That would be $80,483 in today's money. With 100 passengers, you'd be looking at a little over $800,000 per flight. Probably not cost effective with the high expense of hydrogen, but it could have been done. High-value transport like disaster relief or military supplies with an automated ship would have been valuable. Fueling it back up to get it back home would be an issue, though. Hydrogen is tough to find. Liquid hydrogen is very expensive to produce. First, you have to take methane and hit it with superheated steam. Lots of fossil fuel use there, with an energy efficiency of 65%. Then separate out the hydrogen gas and compress it to an extremely high pressure. More energy lost there. Now keep it at only 20 degrees centigrade above absolute zero. It is only economical for space flight with today's prices. But wait, we have hydrogen cars now from Toyota and BMW. And weren't we going to get a hydrogen truck? These, ladies and gentlemen, are a type of scam. Most of rational humanity knows that fossil fuel use is contributing to global warming at an unsustainable rate. These companies are playing off the true need for green energy, saying, hey look, we made a hydrogen-based vehicle. It produces pure water and exhaust, and no pollutants. Don't burn hydrogen, by the way. That produces nitrous oxides, which are a serious pollutant. Run it through a fuel cell. But even then, we have to make the hydrogen. And we could use solar to produce electricity and use the electricity to electrolyze water at an efficiency of 80%. And we still have to compress it with an efficiency of 56%, which leaves us with 44.8%. And we have to keep it cool, say at 10% loss. It gives us 40% of the original solar electric power in hydrogen power. Or we could just use all the solar to charge up our all-electric Tesla. Now do you see why hydrogen energy trucks and cars right now are a bad idea? These companies are saying, look at my one hydrogen car prototype over here, and please ignore my clean diesel cars that produce almost as much pollution as a 1960s freight train. The reason Nikola stock is tanking is because they did not have a revolutionary idea. They did not have an ultra-efficient catalyst to produce the hydrogen. They had hype, a good pitchman, and a trust in the scientific ignorance of the average investor. I believe that Nikola may have chosen its name to associate itself in the minds of the public with Tesla and make people think they were getting in on a great deal. Those of you who invested in Tesla early know that it is really paying off now. A truly competitive company will not name itself in a manner that makes you think of its competition. You never hear about a McBurger King. The goal of Nikola was not to make hydrogen vehicles, but to convince investors and sell stock, hoping that with enough money they could get a breakthrough that would justify the hype. So hydrogen is expensive, and while our 1969 Starship would have probably flown with 1970s technology, landing with the computers from those times might have been a little more interesting. But what about methane? It comes out of the ground as a byproduct of almost all oil production. It can be used in very efficient solid oxide fuel cells, molten carbonate fuel cells, and platinum catalyst fuel cells. It is also about 6 times denser than liquid hydrogen and can be stored at 110 Kelvin instead of 20 Kelvin. If you want to impress me, start making a hybrid methane-based airplane using rechargeable batteries and fuel cells. Charge the batteries before takeoff and run the fuel cell to supplement power for takeoff and long-range travel. Methane is available almost everywhere, and we could just put all those cows into big domes. And we'll get into that another time. Methane for rocket fuel is about as perfect as we can hope right now. So we have shown that while the SpaceX Starship is revolutionary in its execution and innovative in its engineering, this was possible a long time ago. Why wasn't it done? That's a good question. Why do smart people do dumb things? Apple decided not to buy Tesla. Blockbuster decided not to buy Netflix. The Europeans are working on bigger, expendable rockets while SpaceX, with reusability, will kill them on price. If smart people are all making the same mistake for no good reason, what can we do? That's what disruptive technology is all about. Seeing a solution that should have been obvious all along, and having the resources and the will to prove a better way. Thanks for listening. Don't forget to like and subscribe. Please help us out with some tuition at patreon.com/Terran Space Academy. We do appreciate your help during these hard times, Wade. And until next time, stay safe.